Okay, so let me tell you about some of the challenges we're facing in searching for compact binaries with advanced LIGO. And for this audience, I won't try and justify why this is interesting or why we should go after it. I will start with the astrophysical targets we're going after and touch on each of these in turn, tell you the status of what's going on with our knowledge of the searches, with the waveforms, with the template banks, and where we're lacking knowledge and could do with some help, and where we have things well handled. So this is our mass space in component mass, M1, M2. We have binary neutron stars down here in the corner, around 1.4, 1.4. Neutron star black hole, binary black hole. This upper mass limit here is set by the low frequency wall of the detector. In initial LIGO, this was 100 hertz, but in advanced LIGO, it goes up to 100 solar masses. But in advanced LIGO with the lower frequency, this extends up to several hundred solar masses total mass. Now, the low frequency wall extends our parameter space, but it also presents challenges down here as well. We have much longer waveforms, and I'll talk about the effect of the longer waveforms, the increased number of cycles, on what's going on down here in the BNS and NSBH region. So what are we going after? Well, as we all know, advanced LIGO's most likely source is binary neutron stars with a rate varying between 0.4 and 400 per year. The most plausible value around 40, but there's a lot of uncertainty on that rate estimate. We don't have any observations of binary black hole or neutron star black hole systems, but we have two observations of X-ray binaries that they're expected to evolve to binary black hole systems. There's a black hole and a Wolf-Rayet star that are emitting in the X-ray, and through most plausible evolution models for the Wolf-Rayet star, these are expected to form binary black holes. The aLIGO binary black hole rate, again, a lot of uncertainty, right? We have no actual observed BBH systems. We only have extrapolations from population synthesis in these two systems. The rate could be 0.4 a year, or maybe as high as 1,000 systems a year, if you believe some of the more optimistic rates that are coming out of the Belchinski's group. Neutron star black hole, Cygnus X3 is a possible NSBH progenitor, about a 15% chance of that evolving to a close NSBH binary. Again, no direct observations of NSBH. The rate's estimated to be between 0.2 and 300 per year. So these are all the systems we're going after. These are the current knowledge of the rate estimates of these systems. So compact binaries are the most likely source for advanced LIGO. We want to make sure that we have all this covered. So these rate estimates here have something implicit in them. Implicit in these rate estimates is that we can detect these signals at a signal-to-noise ratio of 8 in a detector that can see an average distance of 200 megaparsecs. That requires two things. One is a detector that can actually see 200 megaparsecs for binary neutron stars, and work is ongoing at the moment. Advanced LIGO is being constructed to get us from the initial LIGO and then the eLIGO sensitivity down to the ultimate sensitivity with maybe 15 hertz, maybe 10 if you're lucky, low frequency cutoff, and broadband sensitivity in order of magnitude better. So the first thing we require is detectors can actually see a large volume of the universe. But then we also require, to get that signal-to-noise ratio of 8, that 200 megaparsecs, 220 megaparsecs for binary neutron stars, and then the distances for binary black holes, we need optimal detection statistics. And when you know the waveforms, you can use match filtering and construct an optimal statistic. And I'm going to come back to this a few times. Let me just say it explicitly, but everyone knows it. The A and B is the noise-weighted. This is the detector noise curve, correlation between two Fourier domain templates here, and we can construct a match filter signal noise statistic by projecting the template against the data stream and then normalizing by the length of the template. So we need to have accurate template waveforms to go into this match filter to achieve the sensitivities and hence the rates that we're promising. Non-Gaussian noise transients complicate the search. I won't talk too much about these other than to say that knowing the waveform is not just important for the match filtering, but also for mitigating the effect of non-Gaussian transients if the non-Gaussian transients can't be eliminated in the detector. Obviously, that's the best way of doing it, but we can't go back in time. If there are non-Gaussian transients in there, we have to deal with them. And so knowledge of the waveform can help this a lot. And these techniques were put into place in initial LIGO, a lot of work on developing these search pipelines in initial LIGO. Another thing that is very important to construct the match filter is we don't know a priori what the parameters of the signals we're going to see are. We know binary neutron stars have a mass of around 1.4 solar masses, but we don't know whether it's 1.35, whether it's 1.4, whether 1.27. And so we need a way of constructing a bank of match filters that will adequately cover the signal space that we're searching, and so we don't lose signal to noise, and hence range of the universe, and hence event rate in the sources we're looking for. And the standard method for constructing these template banks, it goes back to work by Ben Owen and Satya Prakash from the late 90s, revised a little bit for the placement algorithm by Satya's group in 2006, is to place a grid of templates using a metric, where the metric tells us how we lose signal to noise as we vary the parameters of the waveform. So if I'm here, I change the parameters of my waveform, I lose SNR, I need to put another template here in order to capture the varying parameters. And if we have a metric that's flat, we can use a hexagonal placement mechanism. This is for a binary neutron star system. Tau naught here is basically the chirp mass. Tau 3 is the mass ratio, related to the mass ratio. If we have a flat metric, we can place these templates in a hexagonal lattice and ensure that no matter where in this space our signal waveform lies, there is a template that is near enough that we lose no more than, give me a number, 3% is the standard number we use. No more than 3% of the SNR is lost by the discretization of the template bank. And one thing it's worth mentioning is that in initial LIGO, all our template placement was done with this method. It was 2pn accurate using stationary phase waveforms and this hexagonal placement technique. Everything we did in initial LIGO used this template placement technique. There weren't any new template placement mechanisms developed and deployed in advanced LIGO. Okay, so let's take a look at the in-spiral waveforms we're dealing with. I'm going to be talking about waveform approximates a lot, so let me briefly review how we generate a waveform approximate. This is the Peters calculation of an inspiral, adiabatic inspiral, at the so-called Newtonian order. I can calculate the energy of the binary, just the orbital energy and the gravitational potential energy and the kinetic energy of the binary, give me the orbital energy at Newtonian order. I can take the Einstein quadrupole formula, and I can work out the time average of the third time derivative of the quadrupole moment tensor and get the flux. Then I can use this adiabatic technique and say that the flux and energy must balance, and rearrange this to get the rate as a function of time. And this is the standard leading order Peters in-spiral rate for a binary. I can then plug that into Kepler. That gives me the orbital frequency evolution function of time, and I get my in-spiral waveform. And when we talk about all these different post-Newtonian approximates, they're basically varying different methods of going from these two quantities right here, the energy and the flux, to actually get something that looks like, my battery's like, something that looks like an in-spiral waveform. So we know that the Peters and Matthews waveform is not the end of the story. That's just the leading order waveform. It gives us a waveform that only depends on the chirp mass, and higher order physics in the waveform affects the phase evolution. The mass ratio affects the phase evolution, the spins, eccentricity, if you believe in eccentric binary systems. These all enter at higher order corrections to the waveform phasing and change the phase evolution of the waveform. And it's the phase evolution that the match filter is most sensitive to. So if we get this phase evolution wrong, then we see less of the universe. A couple of things that I'm going to talk about here. Mass ratio couples into numerical relativity. When NR groups do a numerical simulation, they do it for a particular mass ratio, they do it for a particular spin, but they get total mass for free because the mass just scales out. Eccentricity is something that's generated some level of interest lately. I'll touch on all of these and talk about how they affect advanced LIGO's waveforms. One big issue that I want to talk about is the effect of spin in the waveforms. If the binary is non-spinning, or you can ignore the component spin of the binary, so the angular momentum of the objects, the binary is basically parameterized by the total mass and the mass ratio, or the chirp mass and the symmetric mass, or whatever two combinations of M1, M2 you want to pick to parameterize the binary. When you have spin, you have the component masses of the binary, you have the position of the binary because the binary frame starts to precess, gives you additional complications, both to the waveform you see at the detector from effects like precession, but also to the phase evolution. One thing that's a little bit ambiguous here when you look at this waveform by eye is you say, oh, you see the effect of spin as these big amplitude modulations on the waveform. That's actually not the worst effect. The precession effect in some orientations can give you a bad effect, but the change to the phase evolution, even that you get even in the aligned spin case, where you don't get precession because the binaries are aligned and remain, the spin of the binaries are aligned and aligned with the orbital angular momentum, you get a change to the phase evolution that hurts you for spinning binaries. So when you see these pictures, say, oh, that wiggly stuff is the bad effect of spin, it's actually not. It's the change to the intrinsic phase evolution, even without the effect of the precession that gives you that amplitude modulation in the waveform you see in the detector. And there's a substantial literature going back to the mid-90s and even before. I'm sure I've missed a lot of references here about the effects of spin in binaries for gravitational wave detectors. So I mentioned when I gave you the recipe for constructing the waveform, it started with the energy and the flux. How do we get the energy and flux at higher than just the leading order? Well, we need post-Newtonian methods to construct the flux. And rather than giving you the 50 references, Luc Blanchet's Living Reviews is the best place to go and look. For the methods of constructing the post-Newtonian approximation, you construct higher order Pn corrections to the energy, higher order Pn corrections to the flux, repeat that energy balance calculation, and get another Adiabatic Inspiral at higher post-Newtonian order, where you have higher order mass corrections, spin orbit corrections, spin-spin corrections, as you add in these post-Newtonian corrections to the waveform. We also have numerical relativity that will give us the late inspiral and merger part of the waveform. And we have perturbation theory that gives us the ring down. What a lot of work has gone into lately is calibrating models like the effective one body, which are a different approach, different from post-Newtonian theory. They're based on post-Newtonian theory. The flux in the original EOB models is basically the same as the PN flux you get in the standard post-Newtonian waveforms. But in the newer EOB models, that flux is calibrated to numerical relativity. There's additional calibration terms in there to NR, and that can give you very accurate late inspiral merger calibration that you can then extend down to lower frequencies and give you a complete inspiral merger ring down waveform. And the PAM paper is the latest non-spinning EOB NR version 2, calibrated to the Caltech Cornell spec waveforms. And there's a more recent paper that calibrates this for aligned spinning waveforms. Okay, so that's the background. Where are we with the different searches and sources that we're looking for? So let me start with binary neutron stars. So the binary neutron star searcher better be well handled because it's the source we're going to see. So is it? Well, one thing that, if David Shoemaker's listening at MIT, that I remember he would always say it at LSC meetings is, what about spin? What about spin in the binary neutron stars? You guys always ignore the effect of spin in the BNS searches. And we did because we argued that this was a small effect on the phase evolution. The spin appears initially at 1.5 Pn, doesn't appear at leading order. The spin corrections for binary neutron stars, we don't expect them to be particularly high spin. It's a small effect, and it's negligible in binary neutron star waveforms that only last 25 seconds in the initial LIGO band. So we know spin is a small effect. We did some simulations and argued that we could ignore the spin on the BNS simulation. But in advanced LIGO, with a low-frequency cutoff, and I'm going to pick 15 hertz low-frequency cutoff for advanced LIGO. We can argue later about whether or not that's too high, too low. But everything I'm going to quote here is going to quote a 15 hertz low-frequency cutoff. And starting from 15 hertz, these binary neutron star waveforms last for 9,000 cycles, 160 seconds. That's lots of time while the waveform is sweeping through the advanced LIGO detector's band for small effects on the phase evolution to accumulate and end up giving you, a radian or two at the end of the waveform, which might not sound like a lot, but is enough to have a serious impact on the detection efficiency of a match filter search. So let's ask, how bad is this effect for advanced LIGO? Well, we can take a neutron star with a canonical moment of inertia of 10 to the 38 kilogram meters squared and calculate the dimensionless spin of the neutron star. And it's basically In dimensionless units, it's 0.4 for a 1 millisecond neutron star. So we can model the binary neutron star population with 3 uniform spin distributions. So my spin is going to be uniformly distributed between 0 and 0.05. I pick that as the highest spin we've actually seen in double pulsar systems. That's probably even a fairly optimistic upper limit on what the spins of neutron star binaries will be. I can go up to 0.4, which is my, okay, so maybe there's some mechanism I've not thought about. There's some direct capture in globular clusters where I can get recycled pulsars forming binaries where these neutron stars might be highly spinning. 0.4 is probably the maximum spin of a neutron star from recycling, and 0.2 is my number in the middle to see how bad these effects are in the mid-range. So 0.05 is my, this is what I reasonably expect to see. 0.4 is my, what if there's some formation channel that I haven't thought about, and I want to make statements and understand the selection bias if I don't see, if LIGO doesn't see neutron star binaries with a lot of spin. And I can calculate the fitting factor, or effectualness it's sometimes called, of my search. I can place a template bank. I'll do that with my standard non-spinning search. And I can ask, what's the fitting factor of my template bank? What's the loss in signal to noise from ignoring the effective spin? And I'm going to test this template bank with a couple of different waveforms. You remember I said that I have various different methods of constructing these post-Newtonian approximants. They all have different names, Taylor, Pardee, depending on how the flux is resummed. But all the ones I'm going to be using here are Taylor resummations of the Taylor series and the flux. So they're all called Taylor something. T is a time domain waveform, and 4 is just a counter that tells me which one I'm looking at. So I'm going to model my spinning, processing binary neutron star waveforms with the Taylor T4 approximant, which is currently known to 3.5 pn order in the orbital phase, so that's 7 corrections beyond leading order, 2.5 pn order in spin orbit, so that's leading order and next to leading order, and 2 pn order in spin-spin, which is leading order. There are the next to leading order spin-spin is also known. It wasn't known when we did this study, so we didn't put it in. There are bits of higher order terms known, but this is basically the complete waveform we had at the time when we did this. How do I get this Taylor T4 model? Well, now I have f of v over e prime of v. I expand this. I truncate it to some consistent post-Newtonian order. So I truncate it to 3.5 pn. My invariant velocity is pi mf to the 1/3. And I can numerically integrate these equations to give me the gravitational wave phase as a function of time. So this is one of my PN approximants. It's the one I'm going to use to model my signal waveforms. It's the only waveform we had at the time that modeled precession for spinning neutron star binaries. My template waveforms, I'm going to use the standard Taylor F2 approximant. The flux is the Taylor series, F for a frequency domain waveform, 2 because it's number 2. Accurate to 3.5 pn orbital order. So there's no spin effects in this waveform. How do I generate this waveform? Well, now I have a slightly different rearrangement of my energy and flux. I get differential equation for dt by dv. I re-expand that, truncate it to consistent post-Newtonian order. Again, 3.5 pn order. I can write down a closed form expression for the gravitational wave phase, and I can use the stationary phase approximation to construct a waveform directly in the frequency domain. In gravitational wave searches, when we're actually looking for binaries in practice, we like this waveform a lot. The reason we like it a lot is because we can write it down directly in the frequency domain. That saves a Fourier transform, because if you're searching for these things, you have a bank of waveforms, you have to Fourier transform each one, do the correlation in the frequency domain. So it saves us a Fourier transform, which with a large bank of templates that we get for advanced LIGO saves a lot of computational power. You only have to do one inverse Fourier transform. But also on newer hardware, doing these frequency domain waveforms can be done very, very quickly on GPUs. So you can compute this waveform extremely efficiently on a GPU, do the correlation very fast on the GPU. And so this is our workhorse waveform for a number of reasons. This is why we're particularly partial to the Taylor F2 waveform, and we're always asking the question, where can we use Taylor F2? To search for my systems, I'm going to use, again, the standard 2pn Owen-Sathia bank placement. Owen-Sathia is actually constructed by taking this waveform that can be expressed analytically, writing down the metric, and transforming to a coordinate system where that metric is flat. So how do I do with my generic spinning precessing by neutron star population. We'll have 3 curves on here. This plot here shows the fitting factor of the template bank. So I'm going to drop in a simulation, going to simulate a random binary neutron star system. I'm going to filter it against all the templates in the bank, calculate the highest match between the bank and the waveform. That's the best I'll do. That's my fitting factor of the template bank. So high fitting factors, I want 0.97 for my fitting factor. That's how I constructed my bank. So I want all my waveforms in my bank to have a fitting factor above 0.97. And the y-axis shows the fraction of injections that are less than the fitting factor shown on the x-axis. And you can see that even with a non-spinning search, for this low-spinning plausible distribution, most of the signals are above 97%. So if binary neutron star spins are small, then the non-spinning search will do perfectly well to capture the vast majority. There's a small tail coming out here for the highest misalignments, the largest spins, but it's not a huge effect for the binary neutron star systems if the spin is less than 0.05 for the individual components. However, if the spin is less than 0.4, then there can be a significant loss in the fitting factor. If I look, 10% of my signals are way down in the 25% loss in signal noise. So this can be quite a large effect if I want to ask the question, are there any highly spinning systems out there? And maybe I want to do a little bit better down here and really make sure that everything is above 97%. Yeah. Most of the SNR comes from the bucket. So most of the power of the match filter comes from the most sensitive band of the detector. So most of this is coming for advanced LIGO in the tens of hertz to a few hundred hertz band. That's where all the interesting information is coming from. So this is so if you look at if you look at one of these bad systems, then it's a system that has fairly high spins on the neutron stars, reasonable misalignment, but not egregious misalignment, and it's just differences in the phi of t, the phase evolution, between the spinning precessing binary and the nearest non-spinning neutron star binary. But it's coming in the bucket. For I can answer that question in much more detail for neutron star black hole, and I will in a minute, because it's more interesting in that case. Okay. So I can ask the question, and we did. Okay, this is not bad, but can we do better? Can we go beyond the Owen-Saphir bank, and can we construct an aligned spin Taylor F2 bank that handles the effect of spin in the waveform? And I can say, can I construct a general processing bank? But that's too hard a problem to start with. I'm going to say, let's just do aligned spin. And can I write down a metric for an aligned spin template bank so I can use my hexagonal or AN star, if it's higher dimensional placement, to lay down a grid of templates for the systems I'm missing? If I look at this is the stationary phase function right here. So this is this e to the I psi in the stationary phase. This is the post-Newtonian expansion. I have the leading order phase, the lambda naught. These lambdas are the post-Newtonian coefficients. It's about 4 pages to show all of them, so I'll just show one, lambda 3, to illustrate. This is the 1.5 pn term. It depends on the symmetric mass ratio, and here you can see it also depends on this beta parameter, where beta is the spin orbit parameter, and so this guy depends on the spins of the binary as well as the mass ratio. So I can say, okay, well I have this stationary phase. Can I go beyond Owen-Saphir, and can I construct a metric for it? Can I construct a metric using this aligned spin waveform? And turns out you can. So you can treat those lambda I as 8 independent components of the waveform. Now this isn't physical because there are only really 4 physical components in here. M1, M2, spin of neutron star 1, spin of neutron star 2. But I have 8 terms in the 3.5 pn expansion. I have the 7 the power series terms and the log term that give me 8 terms. So I can just naively say, well, I have this analytic quantity, and I can write down a metric for it. My actual physical waveforms live in a 4-dimensional subspace of this manifold. They live on the space that has physical masses and physical spins. But my 8-dimensional manifold is a bit bigger. I'm not too worried about that. I'm going to reduce down to a smaller subspace in a minute. But this 8-dimensional space actually allows us to construct a metric without intrinsic curvature that allows us to place templates using an AN-star lattice. So we can go beyond O and Sathya and place templates for these aligned spin binaries using an analytic metric, which is much more efficient, gives us the minimum number of templates we need to cover the space. How do we do this? Well, do we need an 8-dimensional bank to cover the aligned spin space? The answer is no. We can rotate and rescale the metric and transform it to a Cartesian coordinate system. Then we can orient the coordinates along the principal components of the parameter space. So we can do a principal component analysis of our metric. We can ask which are the most important dimensions in the parameter space. When we did this, I bet Ian that chirp mass would be the most important one still, and lo and behold, chirp mass still is the most important dimension. But there are other dimensions in there, some of which are important. We know that mass ratio is going to be important. But there are other dimensions in that 8-dimensional space that aren't important. We know it should be no more than 4. So we can identify directions in which the physical space is thin, and no templates are needed in that direction. So we can try and find the smallest submanifold, that 8-dimensional space, where I can place templates and cover the grid. I won't go into the technical details of this. Let me just argue that this is this C1 and C2 are the two coordinates in the template space. This is basically chirp mass, and this is basically mass ratio and some corrections that cope with the spin. And then, so these are the most two important directions in the space, and this z-axis here shows you the depth in the next most important direction. And the take-home message here is that it's the mismatch in the next most important direction, and these mismatches are very small. So basically, the take-home message for this plot is we can write down a 2-dimensional subspace of this 8-dimensional space that captures the effects of aligned spin binaries for the binary neutron star system. So it actually turns out to be even better than we thought. We started with this 8-dimensional space. We think the physical one is 4. It turns out there are only really 2 dimensions in this space that matter, one that is basically the chirp mass, and one that is the mass ratio with some corrections that fold in the spin effects of the binary. So this is great because we know how to place 2-dimensional hexagonal lattices. This is an easy problem. So we can write down this metric. We can figure out what the physical space is. It's 2-dimensional in these weird coordinates, but we know how to transform from these C1, C2 coordinates back to M1, M2 if necessary. We've been doing this for a while with, O and Sathya takes M1 and 2 and turns them into tau 0, tau 3, these chirp times. We just have C1, C2, which are similar to tau 0, tau 3, but include spin effects. And for Stuart, because he cares about these numbers, this increases the number of templates from 80,000 to 500,000 templates to cover the aligned spin parameter space. So the proof's in the pudding. Does this metric actually work? So what we do is we take this metric, we place a 2-dimensional template bank for aligned spin binaries, and we inject aligned spin binaries into the bank. And we ask, have we actually achieved a 97% fitting factor, 97% minimal match, if we construct a hexagonal lattice that's supposed to have 97%? The answer is yes. Almost all, 1 in it, so this is 10 to the minus 3 down here, my fraction of signals with fitting factor of less than 0.97. So this metric works extremely well for aligned spin systems with aligned spin templates. Now I can ask, how well does it work for generic systems? So if I don't restrict to my sources being aligned spin, I expect there to be some supernova kick that can misalign the binaries. Might not be too misaligned, but we're not, there's not a lot of knowledge there about what the alignment of the spins are going to be. And now I've completely solved the problem for my 0.05 population, and things look a lot better even for my 0.4 population, with only a small percentage of the binary systems having fitting factors that are worse than the 97% match of the bank I constructed. So basically, this solves the spinning neutron star problem. We know we can still kind of, we can keep going with the non-spinning search. We can put a few extra templates in there if we really want to bring this down. We actually don't need all the 500,000 templates to get this population. We need the 500,000 templates to get this population here. So you can say, okay, tell me what you think the maximum spin of the neutron star distribution is going to be up to 0.4, which is a good physical limit, and I can give you a template bank which will have no more than 500,000 templates, which is computationally tractable for aLIGO, that will capture these systems. Okay, so that's the binary neutron star problem. Before I leave binary neutron stars, let me say one quick thing about eccentricity, because there's been some recent interest in eccentricity in binary systems. There's been a few papers over the last few years, another one this year, proposing models where you can form binary neutron stars that have non-trivial eccentricity in the LIGO band. So field binaries we expect to circularize. They radiate their eccentricity very quickly, so the field binaries will be circular in the LIGO band. All the double neutron star systems observed as pulsars will have absolutely negligible eccentricity by the time they observe. But there are these theoretical models that have suggested in galactic nuclei or globular clusters, direct capture, CaJAGWR, there may be some of these eccentric binaries out there. And you can argue, they're either a small fraction or a very small fraction or an extremely small fraction of the field binary rate, depending on who you speak to. But let me take the agnostic approach and say, well, we're building an observatory to look at the universe. If these things are out there, we want to either see them or at least understand why we're not seeing them. So we did a quick study that was of what the effect of eccentricity in the binary neutron star systems are, using post-Newtonian templates, which we expect to be valid for binary neutron stars, and injecting signals with distribution of eccentricity up to 0.4, which is much, much higher than the 10 to the minus 4, 5 you expect for field binaries when they reach the 15 Hertz LIGO cutoff. And for the low eccentricity binary, so with an eccentricity below 0.02, there's basically no effect. That it's not 1 because you're just seeing it's a discrete template bank, you're seeing the discretization of the template bank, but above 0.02 for binary neutron star systems, it starts to drop off. Yes, yeah. So so your field binaries are down here, right? So this is if it still has residual eccentricity at 15 Hertz. So this is E at 15 Hertz. So if these systems exist, if these direct capture formations or CaJAGWR resonance mechanisms, then we will need a search that targets eccentric binaries in this region right here. And we're working on basically there's a stationary phase family Nico Unison collaborators came up with that's supposed to model these binaries, and so we're working on basically using similar type of machinery to the BNS search to see if we can bring this up. But this is, given the likelihood of eccentric binary neutron stars, that project is prioritized according to the likelihood of eccentric binary neutron stars. It should be fairly easy to do, so I think we can get it out fairly quickly. No, these are the eccentricity evolves. So this is E at 15 Hertz. So these will continue to radiate eccentricity in the LIGO band. These are basically Peters and Matthews eccentric binary wave. Actually, the waveform reference here is Ian Hinder, and there's a paper by Peter Zimmerman, myself, at Underground Circuits, where we looked at this for initial LIGO, basically using Ian's PN waveforms that were tuned to some numerical relativity simulations. Okay, neutron star black hole binaries. What about neutron star black hole binaries? Not the given source that binary neutron stars are, but a very important source, a lot of very interesting physics. For neutron stars torn apart by a black hole at a significant fraction of the speed of light, there might be some interesting electromagnetic stuff going on, besides all the cool gravitational wave stuff that we expect to see for neutron star black hole binaries. So we can ask the question, how badly does the non-spinning search perform for NSBH binaries? And we said, okay, well, we've just done this nice work with the binary neutron star method. We have this nice template bank. Let's go ahead and we'll just answer the binary neutron star question. And we had an argument, oh, let's do binary black holes. No, let's do binary neutron stars first. And we said, well, let's do neutron star black hole because we know the waveforms for neutron star black hole. We don't have to worry about numerical relativity and all this type of stuff that people are worrying about for the binary black hole waveforms. Let's just take the method that I was just talking about, extend it to the neutron star black hole region, construct an aligned spin template bank, ask how well the non-spinning bank does, ask how well the aligned spin metric does, and see how well this does for capturing generic processing systems. So we said, okay, we'll do that, but first we'll figure out whether or not we have good waveforms. So before we put a bank in there, let's ask how good our neutron star black hole inspiral waveforms are. So let's just calculate the overlap. So we're only allowed to maximize over the time and phase. We're not maximizing over the intrinsic parameters of the binary anymore, not maximizing over mass or spin or anything. And let's ask how good the post-Newtonian waveforms we have for neutron star black hole binaries really are. And when people have done PN convergence testing, the PN isn't a mathematically convergent series. We have higher and higher order terms. So people use empirical methods to look at post-Newtonian convergence. And one standard method of looking at the post-Newtonian convergence is by dropping higher order terms in the PN series. So you can say, and that's how we know the binary neutron star waveform's good, right? We know the BNS waveform in orbital phase up to 3.5 PN. The 3 PN is basically good enough. Adding 3.5 PN is adding a small, very small higher order correction that hardly adds any cycles for binary neutron star waveforms. So we can test convergence by dropping higher order terms and asking if the PN is converging onto a waveform that we trust. Now, this is a bit more tricky with spin. When you only know the leading order term, if you drop the leading order term, you no longer have a spinning waveform. So looking at the convergence of the spinning terms is a little bit more difficult. So what we did is we said, okay, well, we have different PN approximants. We have Taylor T4, we have Taylor F2, we have Taylor T2, we have spin EOB if you want to go beyond just the standard PN approximants. And we can ask, how well do these different approximants converge? So if we try and start with the same energy and flux and try and end up with the same physics, same waveform evolution, does it matter which route we take? And if it does matter which route we take, then that suggests that the PN series hasn't converged. So we use this as a proxy for looking at the convergence, given that we can't do the normal trick of dropping the higher order terms. So we did this, and we were quite surprised with what we saw. So this plot shows Taylor T4 and Taylor F2 waveforms. There's no bank here. Each one of these points, we just pick randomly a point in the parameter space. This is the mass ratio of the binary. We're looking at binary neutron star systems. So we picked from 1 to 3, and then our black hole distribution went from 3 to 15. So this is the mass ratio of the system against the spin of the black hole. We're ignoring the neutron star spin here and basically saying the neutron star spin is negligible compared to the spin of the black hole. So black hole spin -1, anti-aligned with the orbital angular momentum, or 1 plus aligned with the orbital angular momentum. And we can ask, what's the match? What's the overlap between the two waveforms? And you see this color bar here goes between 0, which is basically the waveforms are orthogonal, and 1, which means the waveforms are the same. And it's a pretty depressing picture for comparing these Taylor T4 and Taylor F2 waveforms. In the binary neutron star region lives at small spins, at small mass ratios, just under the H of black hole. Everything looks fine there. But when you get into this neutron star black hit, you don't have to go to very high spins of the black hole or very high mass ratios to start to get significant disagreement between the various different post-Newtonian approximants. So then we said, okay, so how much of this effect is due to stationary phase versus time domain? We have these time domain waveforms, you have stationary phase. So we constructed a new approximant that ended up being called Taylor R2F4 for reasons I don't want to go into. That is basically the stationary phase approximation to Taylor T4. We take the Taylor T4, invert it, re-expand, play with the remainder terms, so everything's at consistent post-Newtonian order, and do a stationary phase approximation. And when we compare Taylor T4 and the stationary phase approximant to Taylor T4, this is for aligned spin waveforms. No precession here, aligned spin. It looks pretty good, for mass ratios we expect. It gets worse up here, but it's not horrendous. So most of the effect comes from fundamental disagreements between the PN approximants. It's not a stationary phase time domain effect. And we check this also with the Taylor T2, which is a time domain equivalent of Taylor F2. So this really is a disagreement between the PN approximants. We looked at spin EOB NR, another way of getting the phase evolution. Spin EOB NR, the NR means that at the end of the waveform, the merger ring down is calibrated to spinning numerical relativity simulations. But early in the waveform, which is what we're looking at here, as Tony asked, where are you getting the power from? Most of the power here is coming from the bucket. It's coming from the inspiral. It's not coming from the piece of the waveform where SEOB-NR was calibrated. Again, we have not very high mass ratios, not very high spins before the match starts to get bad. And this plot gets cut off at 0.6 because SEOB-NR is not yet complete. it doesn't match, it doesn't work for spins above 0.6, which is why this plot ends at 0.6 here. So significant, the take-home message here is significant disagreement between all the approximates we looked at for NSBH. I think I'm prepared to say, we don't yet know the spin orbit and spin-spin corrections with sufficient accuracy for aLIGO. But this is a good thing, right? There's lots of physics in the higher order terms. This makes the waveforms more interesting. If we can figure this out, we can detect, we can do parameter estimation. So it's challenging for detection, but it's good. If we can get, for example, long in-spiral-only NR simulations from the spec guys who are well placed to do this, higher order corrections either from PN for the spin terms or effective field theory. How bad is this? So where do things start to diverge? So this is one waveform family. So where do we need to do these in-spiral simulations? This is a single mass ratio. This is 1.4 solar mass by 1.4 neutron star, 6 solar mass black hole. Spin of the black hole here. Now I'm showing the invariant velocity on the bottom here in the LIGO band. I show frequency at the top. So my waveform starts at 15 hertz, and my ISCO frequency is 558 for this 1.46 solar mass system. Here's V for the PN people or the NR people, frequency for the LIGO people at the top, and I can ask, what's the phase difference between these two post-Newtonian approximates? How early is the phase of these two waveforms starting to disagree? And kind of yellowy green is 1 radian, and my yellowy green region again, is pretty close to the beginning of the waveform. These waveforms are diverging pretty quickly. Yeah. No, I'll get to that. Yeah, can the bank save you is the question you're asking. If you maximize over chirp mass and eta, let's say, can you recover this? I'll get that in a second. But in any case, if you actually want to know, when you've detected, if that did work, if you detected something, you want to know what the parameters are, that this still bites you. Here's the same plot for spinning UBNR. I won't go into this too detail. And here's the plot in terms of, given that I've been showing things in terms of match rather than radians. Again, the take-home message is things are not wonderful for the neutron star black hole waveforms. So I can ask the question Stuart just asked and say, okay, let me put this aside. And I've made my plea to the spec guys and to Chad and to Raphael and people and said, please work on these higher order corrections. What I can do is I can say, okay, suppose I knew the phase evolution. Can I construct an aligned spin bank? And actually we can. And then we can ask, does this capture the effect of precession? Now, I know my phase evolution is a bit wrong, but precession is a different effect, so I can try and separate the two and say, if this phase evolution was right, how bad is the effect of precession? And I can separate this out by making sure I use the same approximate for the signal and the waveform, so I don't have these PN approximate disagreements in NSBH. And that's actually why we came up with the Taylor R2F2 waveform, so we can construct the bank. So, question Stuart asked, does the template bank save you? Are you saved by maximizing over the intrinsic parameters? The answer is no. If you look at the F2 versus T4, this is now fitting factor, so I'm maximizing over an aligned spin bank. My aligned spin bank, I've tested it works for the approximate that it was constructed for, but when I vary the approximate, things drop very quickly down to low fitting factors. So I actually do need to know the waveforms correctly. Maximizing the bank is not going to help me in this case. How do I do? So if I say, okay, well, let me put that phase evolution issue aside for the moment and just ask, can I construct a template bank that captures the effect of precession? And I use consistent post-Newtonian orders, so now I'm just looking at the differences due to spin and not errors in the PN. Then can I use the bank placement method I was talking about earlier to construct a template bank that finds processing signals? The answer is you can. These are the results. This is the average fitting factor for a neutron star black hole, for the neutron star black hole space, where the average is over spin orientations. I've injected systems with random spin, and now I'm searching with my non-spinning template bank. And you can see there's a region of the space where the non-spinning template bank does reasonably well, but my fitting factor is 88%, which is below the 97% that I want. But if I use my aligned spin template bank, for a good chunk of the space now, I'm getting the 97% fitting factors I would hope to see with the bank. But it doesn't solve the problem completely. We still need to do we still need to work on the processing problem to capture the effect of the processing systems. Using the aligned spin bank doesn't completely solve the processing neutron star black hole problem in the region you'd expect, which is high mass ratio, high spins. Things get worse. However, I can ask, what's the effect on my detection rate? So now I can weight that fitting factor by the amplitude of the signals. The signals for which the spin effects are particularly bad are actually the quieter signals. And I can ask, how badly do I do in terms of signal fraction loss? So what fraction of the population am I missing, rather than just fitting factor of the template bank? And it turns out to be pretty good, even just with this aligned spin bank. So across most of the space, so this blue region here, 10% loss in signal to noise is what I expect from my discrete bank anyway. So for most of the space, I do pretty well. But again, there's this region where my fraction of the population loss is going up to the 30%. I need to do a better job of the processing search. But maybe the aligned spin bank is good enough for a hierarchical search where you search with aligned spin templates and then dig in with something like PBCV that captures the effects of precession, but is a more difficult and computationally more challenging search to do. So take-home message from this is precession is still a bit of a problem for some region of the NSBH space. We need to work on high spin, high mass ratio systems where the effect of precession is important. Okay, binary black holes are the, yeah? Oh, it doesn't. So I'm basically asking, given that I'm picking up the SNR from the hundreds of hertz region, the matter effects happen at higher frequencies. And even if this is basically treating everything like a point particle because it's the PN approximation. If I want to measure matter effects and I want to measure matter effects early in the inspiral, I better get the orbital phase and the spin pieces correct. So I have to deal with the NSBH problem. I have to deal with that if I want to measure these 5PN tidal finite size effects as well. But I haven't worried about matter in here at all. Okay, binary black hole systems. The question is, where we know we need to worry about merger ring down for binary black hole systems. Where do we have to worry about merger ring down? And where can we keep abusing our Taylor F2 cheap and cheerful templates that we can do fairly computationally efficiently? So where is EOB NRV2? I'm restricting myself to non-spinning systems now. I'm going to ignore the effect of spin for the moment. And I can ask, where can I use my workhorse templates for the low mass search? Where do I have to start worrying about merger ring down? And with the latest EOB NRV2 templates, this is about 12 solar masses. So above 12 solar masses total, I need to worry about merger ring down effects. Below that, my Owen-Sathia bank, my Taylor F2 works fine for the low mass problem. This is actually consistent with a result from Evan Ochsner, who looked at this with the EOB-NR V1 templates. It's nice to see that still holds with the V2 templates. So the Owen-Sathia metric. So the next question is, okay, above 12 solar masses, I need to use EOB-NR V2. I don't have an EOB-NR V2 metric, right? They're not analytic templates. I can't easily write down my analytic metric for EOB-NR V2 templates. So does Owen-Sathia still work? The answer is yes, it does. For the region between 3.3 and 25.25, the standard template placement works well for EOB-NR V2 for advanced LIGO. So this is great. So we don't need a new template placement mechanism for binary black holes in the stellar mass binary black hole region. We can keep using Owen-Sathia. We can use EOB-NR V2 for non-spinning effects. What about the effect of higher order modes? We went a little bit beyond the earlier study with the EOB waveforms because EOB-NR V2 has been calibrated with higher order modes. Not just the 2-2 leading order mode, but the 2-1, 3-3, 4-4, and that should say 5-5, sorry. So what is the effect of ignoring these higher order modes in binary black hole waveforms in the detection searches? So now we said, okay, let's take our EOB-NR template bank and let's leading order, 2-2 mode only, and let's allow signals be the full higher order mode signals that you get from calibrating EOB against the Caltech Cornell numerical relativity waveforms. And you find that, for the most part, it's not too bad. You don't lose too many systems. For edge-on systems at high mass ratios, you start to lose a significant amount of fitting factor, but it's not horrendous for the impact on your event rate for a uniform population. If I look at my uniform population, if I look at a uniform population of binaries, I'm not losing more than 10% of my binary population, which is what I expect from the discrete bank anyway, by ignoring the effect of higher order modes. I do have a selection bias that I'm not seeing these edge-on systems that have high mass ratios. They're the ones that I'm losing, so I need to do a better job to make sure I capture those, and I'm not worried about the effect of higher modes for parameter estimation, where that's also significant. So you can say, well, why did I cut this study off at 25 solar masses? What about higher order modes? Sorry, what about higher masses? Well, at higher masses, we decided to investigate whether or not we could work directly with the numerical simulations. So we asked the question, I went to Mark and I said, how long a simulation can you do? Give me a number. So we said, okay, 40 cycles. So for what region of the inspiral parameter space does a 40-cycle binary black hole NR waveform give me the complete waveform where I get 99% of the power in the advanced LIGO band? And it's actually a substantial chunk of the parameter space. This region shown here shows the region covered by these numerical simulations. So now I can ask, how many NR simulations do I need to construct a detection template bank in this space? And I have the advantage that an NR simulation for a given mass ratio gives me all different values of total mass. So I can take the Q equals 1, 2, 3, 4, 6 equal mass and unequal mass spec simulations, and I can ask, if I use EOB NRV2 as a proxy for these waveforms, so I can investigate the entire template space, can I construct stochastically a bank that satisfies my usual 97% minimal match? And the answer is you can if you give me one more waveform of Q equals 9.2. So I can actually cover the entire region of this parameter space using only NR waveforms. No fitting, no PN, this is purely NR for a detection search with only one more waveform than we have at the moment from the spec group. And Baylor's running this one right now, I believe. I can ask, what about spin? This was non-spinning. Can I play the same trick for spinning binary black hole waveforms? This is the region where we have Mark's magic number of 40 cycles, tested using SEOB-NR as the proxy for the NR waveform, so I can explore the whole parameter space. As you can see, SEOB-NR is truncated above 0.6, so I can also use these IMR phenom C models to explore this. I can ask, do the existing spec waveforms cover the parameter space with sufficient accuracy? Here's that tested with EOB. Here's that tested with phenom C. And you can see here, these blue regions are two holes in the parameter space where I'm missing a couple of NR simulations. If I have two more NR simulations with a spin of 0.2, I can actually place a template bank that fully covers this space. And I can keep playing this trick. In fact, we're going to iterate backwards and forwards using this trick, expanding out. I've only taken 2 slices through the binary black hole space, the equal mass, the non-spinning slice, and a line spinning slice where I let the mass ratios vary. I have the whole binary black hole parameter space, even just for a line spin waveforms left to explore. So we're going to play this game, go backwards and forwards. This method can be used to guide where to place numerical simulations very efficiently for detection searches, and we're going to push this method further and look at parameter estimation if we have more stringent criteria on the overlap. Finally, let me finish up very quickly by asking, okay, we detect something, right? We've detected a signal. We detect a signal with one of these template banks. Everything I've talked about so far has been geared towards making detections advanced LIGO. We want to detect the signals. We want to make sure we get the maximum event rate out of the detectors that we can for the detector sensitivity and not screw this up because we've messed up the waveforms or the search somehow. But when we see something, what can we do with it? Can we start to look at the parameter estimation? And in particular, can we distinguish between binary neutron star and binary black hole waveforms, NSBH, BNS, BBH waveforms? Well, we know that we get the chirp mass very accurately, but the mass ratio we get less accurately. But there's another effect that's also a bit of insidious, which is that the spin and the mass ratio can be degenerate. So if I have a spinning waveform, it hurts my ability to measure the mass ratio. And when you talk to the supernova guys, they want to know, what's the mass of a neutron star? They want to know the chirp mass. They want to know what's M1, what's M2. So how accurately can we get this? And you can see, because the spin terms enter into the phasing, actually, there's an easy way to explain this, which is if I have a binary that's inspiraling, if I increase the spins, then it inspirals more slowly. If I increase the mass ratio, then it inspirals more slowly. So I can fake the spin effect with a mass ratio effect. And I can ask, how bad is this? How bad is the spin degeneracy effect? And we investigated this for binary neutron star, NSBH and BBH, and it can actually be pretty bad. You can get pretty significant degeneracies between so the first, this shows M1, M2, for a 1.35 signal, and I'm asking what could be mistaken with the signal because of effects of, first of all, just the parameter estimation. If my neutron star spin is 0, I get the usual banana. If my neutron star spin can go to 0.05, it gives me additional degeneracy in the mass ratio that makes it harder to measure the component masses. I can explore this for a variety of systems, and I can ask, what Chirp mass do I need to see the smallest mass neutron star? What Chirp mass do I need to guarantee I've seen the highest mass neutron star? So on and so forth. I can ask, where can I distinguish between binary black holes and binary neutron stars convincingly? There's a degeneracy between BBH and NSBH because the mass ratio and the mass ratio and spin degeneracy. And I can ask, where can I conclusively say I have a BBH? This can't possibly be a system that contains a binary neutron star because both the component masses are above 3.2, which is the causal limit on the neutron star mass. And so I can try and construct regions and say, given my knowledge of the current waveforms, what's my definitely a binary black hole region? And it turns out that, again, as you'd expect, this is very sensitive to the waveform family you use. If you just use inspiral-only waveforms, my BBH, definitely a BBH region is that gray region up there. A signal that was in there would definitely be a BBH. If I add merger ringdown in using the ILMR phenom C, then my definitely a BBH region extends into the larger region. But if you choose spinny OBNR, which we didn't for this study because you can only do it up to 0.6, you actually get, for the regions where SEOBNR is valid, you get a different line. So again, more work is needed, interaction between NR and particularly interaction from NR when we make detections to figure out whether this is a binary black hole or not. And one last comment, that if we observe an EM counterpart, then one of the guys has to have matter in it. That constrains our the mass of one of the objects. So this is an example where an EM counterpart would actually help gravitational wave observations, aside from all the other cool things you can do, by constraining the mass of one of the objects to be in the neutron star region, because it can't be a BBH. At least one of the guys must have matter. Okay, so let me finish off and say, the punchline here is it's been a fun and productive visit. One of my take-home messages is, I should drive down to Cornell more often because it's half an hour drive away, and flying across the country to work with the spec group, I can also drive down to Cornell and but we need more work on the BBH and NSBH waveforms for advanced LIGO. And so we have a fun little productive collaboration going where we're going to interact both for these long inspiral waveforms, figure out exactly how many cycles are needed, how we tune these things, if we can construct in the absence of effective field theory methods, coming up with the higher order spin corrections, if we can resort back to some kind of phenomenological waveform, which we don't like doing, but it's better than nothing, to figure out these NSBH waveforms, or at least figure out the magnitude of these unknown higher order PN corrections. Again, work is ongoing for this, so I don't need to make this plea, but accurate merger ringdown waveforms can help us in many, many ways. Processing binary black holes, we haven't even touched the processing binary black hole search yet. A lot of work going on in NRAR just to get those waveforms correct. And one cool thing is we have this nice method using the matches to guide new simulations. So this is a nice way we can interact and say, can you give me these simulations to fill the holes in my parameter space? It's a fairly efficient way of guiding new numerical relativity simulations. And we only have 2 years to the first science run, so we better get busy. Okay, thank you. Larry?
So you showed some results for that.
No, that's the second part of the study, right? So the first thing we did is said, okay, do the waveforms work, right? If if I pick a waveform family that's completely orthogonal to the signals I'm looking for, there's no point me worrying about whether it works in real data. So the first thing I need to do, and we're kind of going back to the drawing board here. We're kind of taking a look at some, this is kind of the mid-90s work that was going on here for initial LIGO. going back and saying, do we have the right waveforms? Now we have to worry about false alarm rate, right? I've just increased my template bank by an order of magnitude to capture the effect of spin, right? What does that do for my false alarm rate? What we're doing right now is we're taking that template bank, putting it in the neutron star black hole search, running it on eLIGO data and eLIGO data that's recolored to look like early advanced LIGO data, and then eventually 15 hertz advanced LIGO data, and saying, we have tools, we have clustering, we have all these tricks that you do in practice. Do these things actually give you an efficient search where you don't kill yourself with a false alarm rate because you increase the size of the template bank? Because this is a problem we've had before, right? We had in S3, we did a spinning neutron star black hole search. It turned out that when you actually looked at the false alarm rate as well, that you might as well just do the non-spinning search. But I think these are, you're adding more templates in a way that we know how to handle, because you have a two-dimensional space. Yeah, it's more dense, but you're not adding lots of dimensions and phenomenological stuff that's gonna bite you. And we can do the chi-squared really easy as well, which we didn't have before for spinning searches. So we should test that, and we are. For binary neutron stars? So binary neutron stars, probably not that much by going back and researching the older data because of the length of the waveform. Yeah, that's the bottom line. These are small effects. If you only have 25 seconds, they don't bite you. If you have hundreds of seconds, they do. Yeah, there is, and in fact, but one thing is the ingredients. So in initial LIGO, we did everything with the FFT search, right? And we know it oversamples. There are these new methods, SVD, that Kip and Chad and people have been working on. There's also and Drew. There's also the singular value the reduced basis one that the Maryland group have been working on. But both of those require a template bank. Right, you need a template bank that spans a space, and then you plug it into this machinery, turn the knob, and get the reduced basis. Yes. So this work we've done is applicable to both standard match filter searches and these newer searches that try and then, okay, I have a template bank that spans a space. Now you give me the minimum set of that template bank that spans a space. But this is needed as input to both those. So again, come back to Larry's question. That may be a way you can win, right? That you get bitten by the false alarm rate for the FFT search, but something like a reduced basis or reduces the number of waveform templates in an intelligent way, and you can reduce it even further.